Our last subject is the heat of formation, formerly called the standard enthalpy of formation. We call it the heat of formation. This dHf. So this is defined as the amount of energy required to form 1 mole of a substance at standard state from reference form elements. So first, let's get into some of these things. The reference form of an element is generally the most stable form. It could be solid, liquid, gas. Allotrope has to do with like a crystal structure of an element at, this is the standard state, like it says up there. Notice that this is different than STP for gases because it's 25 C, which is room temperature approximately, rather than 0 C. By definition, the heat of formation of the reference form is equal to 0. Okay, let's look at an example. And we're going to look at this in terms of words and variables, and then we'll look at it graphically, which for me, the graphic makes a little bit more sense. But at some point, you need to come back to this slide and make sure you understand that this is how its heat of formation is defined. In particular, this line right here basically illustrates the definition. So for example, for carbon, carbon that is in, this is the allotrope, graphite is considered the reference form. So that means that the heat of formation of graphite by definition is 0. Okay. Right here, what it's saying, let's consider diamond. So if I had carbon that's graphite and I wanted to do a reaction to make carbon that is diamond, the heat of that reaction is 1.9 kilojoules. That's how much heat it takes. Okay. Therefore, the heat of formation of diamond is that number, 1.9 kilojoules per mole. Okay, so what I was saying about this one, this is the definition of the heat of formation for diamond. The heat of formation is defined as the change in enthalpy when you take a reference form, which this is, and you make the substance you're interested in, diamond. That is the heat of formation of diamond. Okay, anyway, that's how it works in words and looking at it, an equation. Heat of formation is in kilojoules per mole. And then this is a good way to think about heat of formation. It's basically, it tells how much energy heat, internal heat, enthalpy, how much energy a substance contains. So this is a way that we can assign energy values to different substances, and then we can do math and figure out heats of reactions from those. Okay, for example, let's look at a table. There are these tables for heat of formation you can look up, and it's kind of, I think people are kind of bothered that it's a delta, but it is just a number. It's a delta because it's defined by that reaction on the last slide. But it is just a number that represents the amount of energy in something. And so notice that hydrogen, that's H2, is 0. That means this is the reference form. And then let's see, what else do I want to show you? If it's monoatomic, that's not as stable, and that's why it's a larger number. So if we had an energy diagram, H2 is down low, that means it's more stable, and just hydrogen that's monoatomic is up there, it's a higher energy form. Okay, here it is. Here's an example graphically. Here I put the reference form carbon down at the bottom. Again, an energy diagram. When you see enthalpy, enthalpy is really a form of energy. Energy stored in a substance. Okay, so let's see. What can we do? So here's graphite. This is the reference form. So we assign it a heat of formation of 0. Okay, and everything is compared to that. You guys, this is kind of just a choice that was made so that we can compare energies among different substances, that we decided we would have these reference forms and assign them as a number of 0, and we're going to compare everything against those. So if we take graphite and we add energy, so this is endothermic reaction, and we get diamond, the heat of formation, how much heat we used, was 1.9 kilojoules, and so by definition that's the heat of formation of the diamond. Okay, and just to make sure we understand, higher on this chart is less stable. So what's that saying is our reference form is more stable than the diamond form. And then over here, I put, well, what if we had carbon in the gas phase? Well, you guys probably know that that's not very stable. Carbon is not usually in the gas phase. And so that's why it's way up here at the top, that the reaction to take the reference form and make the gas is going to require a lot of energy, and so that's why it has a very high heat of formation. Let's look at another graphical example. Can heat of formation be negative? Well, it can. Sometimes we think it can't be because it's defined at 0 for the most stable, but actually that is the most stable for individual elements, not necessarily for compounds. Also, there is an exception for ions dissolved in water, which we're not going to get into too much. But anyway, so yes, you can have a negative one. Here, again, you guys, this is one of those reactions that defines the heat of formation for a particular compound. So these are reference form elements. Reference forms of the two elements that go to make this methane. And so if I look at the heat of this reaction, by definition, this is the heat of formation. It's the heat of reaction, but it will be delta HF for CH4. Okay, and then graphically, again, these are our reference forms here. With a heat of formation of 0, and if I wanted to make CH4 for them, I would have an exothermic reaction to get the methane, CH4, and so in this case, all that means is that the CH4 is more stable than the elements. Okay, it doesn't mean that this compound has a negative energy. It just means, lower on the energy diagram means more stable, and so so it means it's more stable. It's a little fat. So down here is more stable, up here is less stable. So they can be negative like that. Okay, so on this one's kind of a strange reaction because I have monoatomic nitrogen and oxygen, which isn't the normal state. And if they were, I mean, if this were N2, the heat of formation would be 0, because that's the reference form, most stable form. But I just chose to make up a reaction where this is monoatomic and this is monoatomic, and I looked up the heats of formation. And I'm making this product, nitric oxide, nitrogen monoxide, IUPAC name. But anyway, so if I add up the amount of energy in the reactants, so I'm adding up these two numbers to get this, and then I look at how much energy is in the product, I can see that this is going to be an exothermic reaction. And so what will the heat of this reaction be? The change in enthalpy will be, I will just subtract. I'm going to do, so this is final minus the initial. So it'll be 90 minus 722, and I get, well, maybe I should write that, 90, and I get negative 632 kilojoules. Okay, so this is why heats of formation are useful. We can assign it, we'll have a number that represents the energy in our reactants, and we'll have a number that represents the energy in the product, and then we could subtract and figure out the heat of the reaction by comparing those two. So I say oversimplified because I'm really kind of not saying all the ifs and buts and specifics, but the way you can think about it is that the heat of a reaction is basically the difference between these energies. Okay, one more slide here. So why is this useful? Well, like I showed you on that table, you can look up these heats of formation, and from those you can calculate a heat of reaction. On this, so this is the general equation. Of course, the sigma means add them up. If you have more than one product, you will add them all up. Products are final. This is initial. That's why you have the order that you do. Oops. And notice that N is from the coefficients because the heats of formation are kilojoules per mole. So you have to say use the N to say how many moles. And that's it. Let's try a few of those and we're done with thermo.